So, picture this. You're trying to squeeze thick, heavy oil out of solid rock, literally miles beneath the surface of the Earth. We aren't just talking about pumping liquid out of a giant pool here. We're talking about mind-blowing engineering that essentially builds a massive, high-tech chemical refinery entirely underground. Welcome to this explainer. Today we're exploring a revolutionary process that transforms useless, trapped heavy oil into pipeline-ready crude before it ever even sees the light of day. It is this fascinating mix of extreme heat, microscopic chemical bouncers, and just brilliant innovation. Let's get into it.
All right, to understand why we need such extreme engineering in the first place, we have to look at the massive challenge of unconventional oil. When energy companies drill horizontal wells, like the ones in the Bakken Formation you see charted here, they usually start off with this incredibly high rate of production. But look at that curve. That production drops off the cliff, sometimes within just a few months. It's a notoriously steep decline, and it often leaves the total recovery factor at less than 10%. So what exactly is happening down there to cause this rapid decline?
Section 1. The Tight Oil Challenge.
If we zoom in on the microscopic level of the rock itself, we see a stark contrast. In conventional reservoirs, the rock has larger, connected pores where fluids just move around easily. But in unconventional, ultra-tight rock, like shale, the permeability is measured in fractions of a millidarcy. It's literally like trying to sip an incredibly thick milkshake through a microscopic, practically invisible straw. The oil molecules are just tightly trapped within the rock matrix. The oil is absolutely there, massive quantities of it, but the rock simply will not let it flow. Now, you might be thinking, well, why not just pump high-pressure water or gas down there to force it out? Well, in ultra-tight rock, that traditional fluid injection often just outright fails. Because the matrix permeability is so low, injected fluid simply can't penetrate the rock. Instead, the pressure ends up creating injection-induced fractures, or IIFs. The injected fluid acts almost like electricity. Finding the path of least resistance, it completely short-circuits. It rushes straight through these fractures directly to the production well, entirely bypassing the trapped oil. You basically end up pumping out exactly what you pumped in, leaving all the valuable resources stuck underground.
Section 2. Rescuing trapped resources.
Since we can't just push the oil out with cold fluids, we have to introduce an entirely different dimension to the equation: extreme heat. And this brings us to a process called THAI, which stands for toe-to-heel air injection. This is an advanced thermal-enhanced oil recovery method. Instead of just pushing the oil, THAI involves a vertical air injection well and a horizontal production well. They inject air to actually sustain a subterranean fire, an in-situ combustion front. This incredible wall of heat slowly sweeps through the reservoir from the toe to the heel of the producer well. The intense heat thermally cracks the heavy oil, drastically reducing its viscosity, and gravity forces this now mobilized oil a short distance downward, right into the production well.
Section 3. The Underground Refinery.
Okay, so the THAI process is great for melting and moving the oil, but researchers realized it actually isn't quite enough for these really heavy bitumens. We need a way to completely transform the oil's chemical structure before it even reaches the surface. Enter the THAI-CAPRI process. This adds a crucial catalytic stage, and this is where things get truly science fiction. THAI-CAPRI essentially builds a high-tech chemical refinery thousands of feet underground. We are actively upgrading the heavy oil in the dark, under massive pressure, miles below our feet.
Let's walk sequentially through the exact journey of a single oil drop in this system. First up, the combustion front heats the rock to intense temperatures, between 500 and 600 degrees Celsius. Second, this extreme heat thermally cracks and mobilizes the heavy oil. Third, and this is the real magic step, before the oil can enter the horizontal producer well, it's forced to pass through an annular sheath, basically a layer of gravel-packed catalyst surrounding the wellbore. Finally, step 4, the newly upgraded, refined oil travels up the well to the surface.
Section 4. The Microscopic Chemical Bouncer. To really appreciate how this transformation actually happens, we need to zoom in even further, right down to the atomic level. Meet the chemical bouncer that makes this underground upgrading possible. Pelletized nickel molybdenum supported on alumina, or NIMO for short. And this isn't just dirt, it's a highly engineered refinery-grade catalyst. In the CAPRI process, this pelletized catalyst is packed closely around the wellbore. Sitting in a highly pressurized environment, baking at 500 to 600 degrees Celsius, this catalyst interacts with the hot oil, the steam, and the combustion gases, forcing these incredibly complex chemical reactions to occur right there inside the rock.
Now, the NIMO catalyst possesses 3 critical superpowers. First, hydronitrogenation.
Yeah, try saying that 3 times fast. Essentially, it is incredibly effective at breaking tough carbon-nitrogen bonds, literally splitting nitrogen atoms right out of the organic molecules. Second is aromatic saturation. Nitrogen is often stubbornly trapped inside these complex ring-like aromatic structures, and NIMO excels at breaking those down. And third, impurity rejection. This one is massive. The catalyst forces the oil to shed all the bad stuff, the coke, the sulfur, heavy metals like nickel and vanadium. But instead of bringing that toxic sludge up to the surface to be processed, the catalyst leaves those impurities behind, trapped forever as an inert residue directly on the underground reservoir rock.
So, you might be wondering, why do they use nickel molybdenum specifically rather than a common industry catalyst like cobalt molybdenum or COMO? Well, while COMO is great for standard sulfur removal, NIMO acts entirely differently under these intense underground reservoir conditions. Through a complex chemical handshake, specifically chemosorbing by proton donation, NIMO proves vastly superior at saturating those complex aromatic rings and breaking the carbon-nitrogen bonds we just talked about. It alters the cracking mechanism in a way that COMO just simply cannot match when it's buried miles underground.
Section 5. A greener extraction future. Zooming back out to the macro scale, we can see the real-world impact of all these microscopic reactions. The crucial takeaway here is the massive leap in quality, which the industry represents by API gravity. Higher numbers mean lighter, much more valuable oil. The standard THAI thermal process, all on its own, increases API gravity by about 8 to 10 degrees. But when you add that CAPRI NEMO catalyst layer we just discussed, you get an additional 6 to 8 degrees right on top of that. Combined, we are looking at an absolutely incredible 14 to 18 degree leap in API gravity straight out of the ground.
To put that into perspective, this combined process successfully upgrades thick 10-degree API bitumen into a light, low-viscosity product of 22 to 24 degrees API. And why does that specific number matter? Because 22 degrees API meets typical pipeline requirements. Normally, energy companies have to buy expensive light liquid diluents to mix with their heavy oil just so it can physically flow through a surface pipeline. But by refining it underground, it comes out already pipeline ready. This represents an absolutely immense economic and logistical victory. We're talking about saving massive amounts of money and surface infrastructure.
And honestly, the benefits go well beyond just economics. Let's compare THAI-CAPRI to the traditional thermal method, steam-assisted gravity drainage, or SAGD. SAGD requires boiling massive quantities of water to create steam, resulting in huge greenhouse gas emissions and really high freshwater use. THAI-CAPRI uses zero water during production, literally zero. The energy comes from burning the waste coke directly inside the rock. Furthermore, SAGD needs very thick reservoirs, over 130 feet, while THAI-CAPRI can operate in thin reservoirs down to just 6 feet. Consequently, THAI-CAPRI has a much smaller surface footprint and a vastly lower overall environmental impact.
Which brings us to a fascinating thought I want to leave you with. We've seen how chemical catalysts and combustion can turn a dormant underground rock formation into an active, self-contained refinery that traps its own waste and requires no surface water. It completely flips traditional extraction on its head. So, if we can successfully refine heavy oil miles underground, what other heavy, dirty, industrial processes can we bury in the future to preserve our surface environment? Thanks for joining me on this explainer. I really hope this sparked your curiosity.